Your main goal for this current video is to be able to convert between Cartesian and cylindrical and Cartesian and spherical. So let's just start with Cartesian and cylindrical. So there are two components that for each of these coordinate transform pairs, there are two things that you need to be able to do. First is to convert from one to the other, and then the second is know the unit length of each of these coordinate transforms. So I'll just start by graphically looking at what the cylindrical coordinate system is, assuming that we're all clear on the Cartesian. So for the most part, I'm going to orient all of our drawings in this form, where we have the xy plane over here and the z-axis running vertically. And the cylindrical coordinate looks a little bit like this. So for any given point up here, you're going to describe it in terms of the unit vectors of rho, which is a radius that comes out of the z-axis, z, which is the vertical coordinate, and then also a phi coordinate, which kind of rotates counterclockwise with 0 degrees being the x-axis. So let's just take a look at a few key points here. To figure out what each of these are, what you would do is, first of all, for the z-coordinate, that's pretty straightforward. That's just this height here. To find rho and phi, what you first do is you project this onto the xy plane. So you project this point onto the xy plane. That's a projection there. And then you basically just draw it out in terms of you project it down to the xy plane and look at the vector that goes back to the origin on the xy plane. In that case, the distance to the origin, that's going to be your rho, and the angle here is going to be your phi. And so in this case, if you were to then take this and project it to the x and y axis, this would be your y coordinate, this would be your x coordinate. So graphically, this is how you move back and forth. So by staring at this, you can kind of figure out what the conversion between coordinates is. So let's just start with the conversion. So so let's start with Cartesian going to cylindrical. So rho is going to be equal to, if you take the Pythagorean theorem, of x squared and y squared. All right, so rho is going to be the square root of x squared plus y squared. Phi would be this angle here. So phi will be defined as the arctangent of the opposite, which is y, over the adjacent. So arctangent of y over x. And remember, make sure to draw this out. Well, don't just punch this into your calculator, but when you get the result, make sure that you draw it out and that the phi that you choose makes sense. So specifically, so one particular point is that arctangent of y over x, if you just plug it into your calculator, it's the same value as arctangent of negative y over negative x, right? So your calculator can't necessarily differentiate between the two, even though one's over here and the other is kind of on the back side there. Similarly, the tangent of minus y over x, where the y is negative, will also numerically be the same as the arctangent of x over minus y. So it doesn't, when you just plug in the arctan, it doesn't necessarily take into account where the negative sign is, even though if you're looking at the xy plane, they're in different places. So you can also write out a little formula where, if this is the x and y, for each of the coordinates, it's always the same deal in terms of whether you need to add from pi, subtract from 2 pi, or just pull the value off the calculator. So I'll leave that to you to work out, but for me personally, I think it helps to just draw it out every time to make sure that you're choosing the right value of phi. And once you do that a few times, you will realize that you won't have to anymore. And then z is simply z. And if we want to go the other way, the x-coordinate, if you're going from cylindrical to Cartesian, you can see the x-coordinate will be rho times the cosine of phi. So rho cosine of phi. The y-coordinate will be rho sine phi. And you can also see that graphically. If this is our angle, this is the long side of the right-hand triangle. And then z is also z. So this set of equations here will give you the ability to freely convert between the two coordinate systems. Now separately, the other thing that I wanted you to be able to do is know the unit lengths. So what I mean is that when you're trying to do an integral, you would have, in the case of Cartesian, this is pretty straightforward. If you wanted to do a line integral in the x direction, your unit length, your little line segment that you would then add up in the course of an integral, is dx, y would be dy, and z would be dz. So it's pretty straightforward in the Cartesian side. But for the cylindrical side, you have to deal with the fact that phi is not in units of length. So if you think about it, z is in units of meters, it's an actual length. Phi is in units of meters, but rho is in units of radians. So how do you change this into unit length? Well, in this case, we'll use the fact that what we want, if this is a circle with the z coming out, and this is x, this is y, what we want is to define this little segment, this little arc segment. So way back when you were learning about arc lengths, you can also recall that if you wanted to find the length of this arc here, that you can do that by simply multiplying the angle in radians by the radius. So if the radius is rho, if you multiply it by the angle d phi, let's just say it's a very short angle d phi, you get the length of this little arc segment here. And another way to remember that is, another way that kind of makes sense is if you have a radius of 1, if you go all the way around, you should get 2 pi, right, times the radius, and that gives you the circumference. So knowing that, you can see that rho would be a short segment of rho will just be d rho because it's in units of meters. Z would be in units, would just be dz. However, if you want a short segment of phi, you need to take the angle, just d phi, but in order to convert it from units of radians to units of meters, you need to multiply it. Remember, radians is basically unitless, so you need to multiply it by the radius, rho. So rho d phi. So anytime you do an integral, if you're trying to integrate across rho, you just put in d rho, z, you put in dz. But it's really important, if you're trying to integrate over phi, you need to multiply it by rho first. So let's just use that to do our first vector integral. Let's do the volume integral of a cylinder. So when I'm doing a volume integral, I'll do 3 integral symbols here. dv means that it's going to be a volume integral. So now you just have to add in the individual segments. So in the case of, let's just say it's a cylinder of this height and radius a. Okay, in that case, it's a volume integral, so you know that you're going to do it off all 3 variables. So for the radius, you do d rho from 0 to a. That's how you draw out a cylinder, right? Let's just start out with going from 0 to a. And then next up, let's rotate the a all around to form the base. So the next variable that we'll do is d phi, and we're going to do it from 0 to 2 pi, rotate it around. Now remember, this is not a unit length, right? So what do we have to do? We need to multiply it by rho. So we'll put the rho in here. And then finally, once you have this part drawn up, you're going to extend it upwards, right? Kind of drag it upwards in the z direction for length h, and then you get the whole volume. So then you integrate it with respect to z from 0 to h. Or if you define your origin here, you can go from minus h over 2 to h over 2. You should end up with the same value anyway. So if we evaluate that, we're going to have 0 to h, and then 0 to, this is dz, and 0 to 2 pi of d phi. And then for rho, you're going to get 0 to a of rho d rho. So the integration of the z part will just be z evaluated from 0 to h. The phi part will be phi evaluated between 0 and 2 pi. So these two values will just be h and 2 pi respectively. And then rho, if you integrate rho, you're going to get 1/2 rho squared, and you go from 0 to a. And so the first term, the z term, is going to give you an h. The phi term is going to give you a 2 pi. And then the rho term is going to give you a 1/2 a squared. Multiply these together, you're going to get h pi a squared, which is how we would calculate the volume of the cylinder, right? It's pi r squared, which is the area of the base, and then multiplied by the height to get the volume of the cylinder. So you see, this allows you to derive the volume of a cylinder using first principles. And now next up, we're going to do the very same thing, but with Cartesian to spherical.